Anyway, so we've recreated the New Zealand population in a digital replica. It's kind of because I think I spent too long playing SimCity 2000 when I was younger. And the likes of those games. And throughout the process, both through the generation of our digital copy of Kiwis and also through some of the code that we've been writing, we've used AI throughout the process. So it's in the back end, in the API, in the chat capability, in the front end, and how we wrote the code. I really don't have enough time to give you much of a demo here, but basically I'll give you a quick view on our initial Population Explorer. So you click a map, it talks to an API, it figures out where that longitude and latitude are. It zooms into a suburb. At that point in the suburb, you see there are lots of locations, households, businesses, employers, supermarkets, shops, fast food restaurants. For each of those modelled locations or modelled agents visit throughout the day. So here we clicked on a supermarket, think New World in Polytechnic. It shows in terms of our model, where did those agents come from? What time of day did they visit that location? And then we can use that for things like modelling the impact of things like what would happen if we had a measles case, where did people come from? Also, what would happen if we implemented different type of policy, if we built a new school in an area or saw a suburb grow. So those little smiley faces, I've lost that page, but that was our individual agents moving around. Okay, so we've been using things like AI. So this little blue button in the corner gives you an overview of, here's a suburb, and then give me a chat agent which you can interact with, you can ask it questions, and then you can click that button at the bottom, export doc, export to Word, and that basically in the browser converts the chat history, as we're building kind of large language model prompts, to a Word file that looks like that without one of my images. Hey ho, it's all good. So that's the export file as a Word file and just kind of generated in the browser. So how did we build that? First of all, ALMA has a very extensive API behind the scenes. Part of that API is how we've generated some prompts to LLMs that specify in very good detail kind of how to respond in terms of text, in terms of tables, in terms of charts. So at the bottom there, kind of there's an example of what we'd say for a pie chart. So when you saw that overview of a population and a bar chart, this is a quick example of what it looks like. So our first block of data back from the large language model is a text block, as you see at the top, overview of population. Then we have a table. I think probably, I don't know if I got the pointer to it. Then we kind of have a bit more text, and at the bottom we have a bar chart, a chart and kind of various charts that it can support. So nice interactive charting capability with that large language model sitting on top. Just generally, digital twin's amazing because it works anywhere on the globe. So we've already built a digital twin of Tonga, and it looks really pretty for overseas. Tonga kind of makes me want to pack my suitcase. Mohammad, I don't quite know if you're going to talk about environmental observations, but here's about 10,000 polygons in Auckland showing some temperature. Some other stuff coming out at the moment. We've just been working on disruption modelling. So say in this case we were planning for maybe a tsunami or what we'd have to do if we needed to evacuate an area. So we've built things like the capability to draw a polygon, and then again, once we finish drawing that polygon, adding a button which allows you to summarise some of the ALMA data for that area. And again, you'll see in a second that chat agent pops up and it starts saying this is the number of roads within that polygon, this is the type of locations within that polygon, and then for our model, for this specific area, this is how many people are at this area at different times of day. So I guess in that area you've got lots of people there at households overnight, nobody goes to the department store at 2 a.m, and then at different times of day. So then you can ask the LLM things like what would happen if we needed to run a tsunami at 11 a.m. and help me write a kind of press release or something. So that's really cool, and again you can export that to Word or whatever you want to do. Really, one thing I really like about working at PHF is that we have a constant stream of students. So at the moment I have two amazing students down at Canterbury. Ivy is helping us to calibrate some of our models around how people use public transport. So this is for Wellington. The chart on the right shows the data for people using public transport from from what we've modelled versus what we see when we look at public transport real-time APIs from the likes of MetLink. So we're kind of trying to just work on the calibration for that. My second student, Andrew, is doing this amazing project building community health and wellbeing profiles to really help areas and decision makers to interpret data in a slightly different way. So if you don't want to build a kind of whizzy 3D map thing, have it as a PDF or a Word file. So really quick, because we'll probably get slightly running out of time. So basically, lots of stuff already done. I think some of my colleagues are going to talk to you slightly more about some of our amazing future work, but it's all go. And shout out to those guys at the back. Thank you. And I guess the thing is that ALMA is just one AI product that we have in public health and forensic science, but actually there's lots of other use cases that we'd see for AI in health and the like. So talk to me in the breaks.
I work at Victoria University of Wellington, and today I'll be talking about my research that I've been doing for quite 9-10 years, particularly using evolution machine learning, basically genetic programming for healthcare applications. So I'll be focusing on how GP can be used in many different ways because of its flexible representation to provide some support around decision-making for clinicians in their healthcare settings. So my research, it focuses on 2 cancer detection domains, skin cancer, including melanoma detection using dermoscopic images, as well as standard camera images. Also, breast cancer detection using mammograms and histopathological images. So before we go into the application side, let's have a quick overview of genetic programming, which most of you have an idea here. So GP, it's a bio-inspired evolutionary method. It's based on Darwinian's principle of evolution and natural selection. And so basically, meaning it works like the natural evolution using selection, crossover, mutation. So it automatically evolves models, or you can say computer programs for a given task. One of the key strengths here is its flexible representation, and that allows us to incorporate domain knowledge, which helps guide the evolution towards better solutions. It can evolve formulas, rules, or even feature transformations. Importantly, it evolves interpretable solutions. So unlike black box architectures, you can actually examine the final programs or trees and understand how it makes decisions. Cancer incidence, very, very important. Skin cancer is the most common cancer in Aotearoa, New Zealand. Each year we have around more than 90,000 non-melanoma cases and around 2,800 invasive melanoma that are diagnosed. On top of that, the annual cost for skin cancer, it has exceeded around $450 million, and it is projected to rise to nearly 690 millions by 2050. That's a lot. In 2022, 535 deaths were reported from skin cancer, 317 from melanoma, and 218 non-melanoma. So early detection is critical here in order to save lives and also help in reducing the healthcare costs. So I'll be going on different methods that we have utilized GP with its flexible representation for the 2 domains. So melanoma detection here. Here we have combined 2 types of features. So first here you can see the domain independent features, basically using local binary patterns or other texture-based image descriptors. And here we have also trying to extract domain knowledge. So this is ABCDE rule of dermoscopy. So kind of asymmetry, border irregularity, color variation, diameter, how big or small, and evolution, how evolving that mole is over time. So, and then this information is combined together Here we are using multi-tree GP, so one solution is having multiple trees here, and each tree is evolved based on one particular type of features. So GP evolves multiple classified trees, and we select the best performing one based on the accuracy. This method outperformed the conventional machine learning methods and also remain interpretable. We will look into interpretability more here in this method. In this work, we have used genetic programming for feature selection. So there basically we have two stages. First stage for feature selection, which is GP's intrinsic capability, and then we have second stage for feature construction, and we combine them together to form this selected and constructed features, and then we give it to the machine learning classifier to get the accuracy. Important thing here is that we found that the selected LBP texture patterns, they show corners, and those corners, particular ones at different scales, they are highly informative to the clinicians, and streaks, and they are associated with malignant lesions. So this information is highly valuable to the dermatologists. This is another work where we have used multi-tree GP to do different things, feature selection, multiple feature construction, and also ensemble model generation. We have developed, so one solution has these 5 evolved trees. I cannot go into the details of them. We have we have used strongly typed GP for automated scale selection, because scale is important, because different patterns appear at different scales. So, and also we have those interpretable trees to look that can perform informative features. Another method, again, clinical information is concatenated together with the image features, and then we have breast density classification, where we have used wavelet-based features, and they have provided quite informative features. And again, the oriented gradients from the Hawk features that had helped GP to evolve better solutions. From histopathological data, we have again developed this multi-tier approach, this structure of GP, to help identify particular patterns inside histopathological images, which are quite dense tissue images. Thank you. Thank you very much.
Tēnā koutou katoa. My name is Farhad. I'm the Research Director at Otago Polytechnic, Auckland International Campus. And today I'm going to present our research project, joint project, which is around Federated and culturally grounded AI for supporting hidden evacuees and disasters. So this project is sponsored by Royal Society of New Zealand. It's a joint project between different countries. I have colleagues from Japan, a company and a university in Japan, from Australia, Germany, Maori advisors from New Zealand, and one of my colleagues, Karitian, is here today, and from Auckland Council, from Massey University, from Waikato, and from my institution. So we are leading this project from OPIC, and the purpose of this project is to, I'm not sure which page I am. Okay. Yeah, is to build basically a framework for supporting people who are using their cars or homes during natural disasters. And this is basically like evident when there was an earthquake in Japan, in Kumamoto City, and Noto Peninsula in Japan again, and the Cyclone Gabrielle in New Zealand, and many people left like in rural communities isolated. and the power internet connections all cut off for a few days. And these hidden evacuees basically need support. They might face dehydration, trauma, and untreated medical conditions. So the idea is to support these people, these evacuees who are staying in their home or cars. And around this project, this is already kind of implemented in Japan, in Kumamoto City, after the earthquake in 2017. But now our idea is to bring this technology to New Zealand, adopt it, and enhance it with some sort of cultural safety and data sovereignty aspects. And one of the issues is about the privacy of the people and data privacy and data sovereignty. So the idea is to use technology like federated learning and differential privacy. So we will enhance the existing system implemented in Japan and New Zealand using the basically cultural and privacy enhanced methodologies. This is also to strengthen the global collaboration between these countries for future projects. So the current system is kind of using different technologies like IoT, mobile data integration for decentralized monitoring, which is implemented in Kumamoto City. And we are going to enhance the system with federated learning, with differential privacy and governance layers, and also having support for multilingual and cultural responsive prompts. Another idea is to use the simulators for understanding the needs of the people who are basically called hidden evacuees. In terms of the collaboration, as I said, so this is going to be a 2-year project. We have just started the project. We have built the initial sort of plan, and for the next stage, what's going to be delivered is a kind of framework and prototype for, so yeah, 4 minutes. Prototype architecture and ethical governance protocol for the first stage. And as a broader application, applications beyond the existing system, like for remote health monitoring and aged care resilience and other sort of systems. And this is also aligned with the United Nations SDGs 3, 10, and 13. And this can also position New Zealand as a global leader in culturally grounded ethical AI for disaster resilience. Thank you so much.
Hi everyone, my name is Mohammad and I am one of the senior data scientists at PHF Science. As my colleague previously explained, ALMA, so this is a platform that we have been developing for quite some time now. And in this particular project, I would like to share one of the projects which we are spending a lot of time on, which is the utilization or development of an integrated agent-based climate risk and adaptation model. Using ALMA as a platform. So as you all know, heat and pollution, heat and pollution have a negative impact on human health. And so in particular causing things like increasing the risk of heart damage or heart attacks, as well as having other issues in terms of heat exhaustion, heat stroke, respiratory issues, and cardiovascular complications. And in particular having an impact on specific groups of people within New Zealand as well as globally. So what we wanted to do within ALMA is to develop a methodology or a model which we can essentially measure and kind of develop policies or help develop policies to address this in a more meaningful way. So quantify and adopt policies to reduce these impacts. Here is ALMA again. Now you should all know what ALMA is. ALMA, is at this stage quite a sophisticated piece of software. And for this particular project, we are utilizing the synthetic population, which is the backbone of ALMA, as well as the diaries, which essentially simulates the movement patterns of synthetic people or agents throughout New Zealand. So we have access to 5 million individuals, but really our area of interest in this case is the Auckland region, which we are working very closely with the Auckland City Council to get data and enable, essentially, develop policies that are relevant to their requirements. So really a synthetic population, briefly explaining it, is a statistical representation of individuals within an SA2 area, having information in terms of age, gender, income, location, and other information. And this can be expanded upon based on information that we have at the SA2 level. So to ensure people are anonymized, we don't really actually use any data. It is just an aggregated representation of people within that area of interest. And the beauty of this approach is that using large language models or and time utilization surveys and time use surveys, it is possible to simulate the movement patterns of different people. If a person is going to a pack and save, or they're going to the gym, or they're staying at home. So we have access to that type of information. We can simulate hourly basis movement patterns of different people. And what is the key advantage of this is that at this stage we have latitude and longitude information to each of the agents. So are they going to go to a specific location, and we can associate any other georeference data to that particular agent, such as remote sensing instruments or remote sensing data, being air quality, being temperature, and so on and so forth. So at the moment we have access to a lot of remote sensing data. Again, we can have access to any georeference data. In this particular case, we are using SO2, PM2.5, nitric oxide, temperature, and because we have the movement patterns of each agent, we can calculate the mean exposure to each agent throughout the year at any different years. So in 2022, for example. So having this information, it is possible to calculate the mean exposure and utilize this to assess health risk or productivity loss according to other research, so health researchers, essentially. So you can see at the top right-hand side, associating for, this is a sample of group of agents that we have within the Auckland region. So you can see that specific agents throughout the year are exposed to significantly more amount of PM2.5, especially around the Auckland city centre. So having that information, it is possible to kind of calculate which groups of people are more at risk and which SA2 levels. And what's interesting is that actually drawing the histogram of the exposure of each of the agents to PM2.5, you can see that there's a significant group of people who are exposed to more PM2.5, which is extremely higher than what the WHO essentially recommends, which is, I believe, PM2.5 of 5 micrograms meter cubed. So the way that we can essentially utilize this is that for each of the agents, we have a specific value that we can derive precision risk assessment for. And utilizing information in terms of DALI values, which we are using from HAPPINS, it is possible to calculate the attributable fraction of risk. So essentially, if a person is exposed to more than 10 micrograms meter cube, what is the associated risk for that person? So this can be in terms of cardiovascular hospitalization, restricted activity days, or overall social cost. And we can repeat this for different pollution values or different values of interest depending on what our colleagues need at the Auckland City Council. So using this information, we can go a step further and essentially simulate which areas are more at risk, which SA2s, and essentially from those SA2s, what type of policies we can adopt if we reduce the risk or reduce pollution by 5% or 10%, what is the overall impact going to be in terms of dollars or overall health impact? And I think in terms of taking this a bit further is to essentially include more health data within the synthetic population, which we are having a bit difficulty with at the moment. So I think that is the next stage that we want to take this, as well as improving working more closely with the Auckland City Council.
Kia ora koutou. I'm Hamid from Unitec. I'm a professor in the School of Computing, and so I'm here now to present our work on developing a multi-phase framework for AI systems, or for the fairness in AI systems. So it's actually not just my colleagues or Mano Chitra Lanka Natan, so just she was my master's student, and we also had a Maori advisor, Diane Tamati, helping with that research. So that is just the earliest steps towards the kind of the proposing framework for the fairness in AI systems. And then, so just as I've been here for a few years now, so my previous, usually not just my background is in speech processing and image processing and working on a voice impairment. And now now I'm moving now towards now just seeing a kind of a big picture. However, this morning now there was a presentation on the fairness, and it says that, there is no issue now with or not much of issue with the fairness, but however, now just we've done a bit of analysis just to exploring that what's going on the current context. So the first thing is, so the first thing is that now just why it matters. And so as you know, now AI is now currently embedding in most of the predictions for the decisions that shape our lives, from employment to finance systems to healthcare to social services. And then as you saw, now just there are just the headlines on the news now just in healthcare. For example, now just Health New Zealand drops tool that just factor in ethnicity for waitlists despite review findings. So in hiring, the issues, the finance issues. So there is still some issues there. And that thing is particularly important in New Zealand context. Why? Because now also it's not only a technical challenge, it's also not just we are now obligated or committed under the Treaty of Waitangi for providing kind of the equal opportunity and equal outcome for the indigenous people in New Zealand, Aotearoa. So if not just our AI systems are trained on an imbalanced data or the bias data, then so just the risk is that so they reproduce that kind of the bias in the outcome, and also now they might also amplify that issue. So now just there have been lots of research now just has been ongoing in international context now to address that, as you saw some of them in the morning, that the issues can be addressed differently, but the main issue is that triggers me now to start working on that research, particularly now just having a student working on it, is not just we had a very limited cultural context, so there's no New Zealand data, or very minimal New Zealand data set have been explored for that purpose, and also now just we don't have and the current approaches are fragmented across the machine learning pipeline. So we try to come up with some kind of the full version of the or full cycle of the machine learning deployment approach. So what we need now just first to do the evaluation and to explore further is a data set. So we use some publicly available data set from US Census, and also now we work with the Stat New Zealand through the IDI lab, Stat New Zealand, to have the census data, New Zealand census data 2023, and also ACC claims. And there were also not just lots of other data sets that we did the experiments on, but these are the notable and significant ones. Also we use a Taiwan data set for the financial data, and we also use some metrics. So these are the just commonly accepted statistical metrics that can be used, and then so just two of them, like for example, statistical parity differences, it actually now, and DI, which is a disparate impact. So mainly they are working on the positive rates, and one of them is the difference is the probability, is the difference probability between privileged and unprivileged when our model predicts a positive outcome. So the difference, so the ideal should be 0, and the DI is the ratio of that probability, and the ideal is 1. So the other two, it actually now just represents the differences in the equal opportunity on the positive rates or the outcome. And then we also tested on the accuracy and balance accuracy. Then the strategies that we use, so there were 3 strategies. One would be on the pre-processing, mainly reweighting or changing the importance of the metrics, and in processing, which was the adversarial debiasing, and mainly means that so not only using the model training, we also use the adversary model to predict the control model. And the aim is now just to train a model in a way that the adversarial model cannot predict the predicted model. Like for example, just previously, we had, for example, is the income or readmission depending on the data set. And that is the in-processing one. And then finally, we also have the bias reduce outputs, which actually now just try to just adjust the thresholds when we have the thresholds for the decisions. And then we use the four algorithms. So just very basic algorithms on random forest and the light GBM, and two other was the TabNet. And I don't remember the fourth one anyway. But now these were not just the algorithms that have been used, and these are not just some of the results that we get now just by applying the whole. The notable, some of them now, for example, for ACC there was no significant really biasing, but there are still bias, like for example in AINZ census data set, so on random forest now just still so just the disparate impact, and the EOD now just these are now just the improvement that has been made. So these numbers are dramatic there. Back to your 10x one. So the trick is that now use a baseline which is 0.01 and make it 0.02. That is 100% increase. So and then you can have that kind of the numbers there. So yeah, there's still the issue is there, and these are just earlier steps to address them. Yep. So that's all from me. And then if you want now just the full set of the experiments and the results and the exploration of the different methods. So just if you can scan that, so it goes to the thesis. I think it was all the experiments there. Thank you so much.
Hello, everyone. My name is Samuel. I'm a student at the Victoria University of Wellington, an employee at Nelson AI, and this project is of a bigger, or this tool is of a bigger project, which is called AINZ, which is from Europe. So first, thank you to everyone there, and NAI and Victoria. I'm going to talk you all through a little bit how AI can assist in invasive aquatic species management. So let me first talk you through the problem and how AI can assist even. So what you can see here is the red crayfish, and this is a very invasive species that is very common now in Europe and originally comes from the US. What it does, it burrows itself inside of dams, and it breaks down the structural integrity of a dam, which can eventually cause floodings like this. So when an invasive species like this is detected, the very first step is often collecting data to see what kind of behavior it does, like this, for example, see if it even does any kind of damage. And that is the kind of the problem. All of the information is incredibly dispersed on these invasive species. There's many different databases, and none of them are normalized. Some of them are in different languages, some of them are hyper-focused on different locations, while all of them use slightly different terminologies. What I mean with that is, for this same species, there's around 4 different Latin names, which is kind of hard if you want to do a full report on a species like this. What this creates is current research is very slow and very resource intensive. So let me introduce you to the tool AINZ Information Assistance System, or GIAS for short. Our goal is simple. We want to make this very first step, which is making a report about an invasive species, faster. How it works is it is split up in 3 different steps. The very first is a dashboard overview. What it does, it goes through all of these trusted databases, connects it with APIs, and then an AI categorizes that into one big aggregated database. Through the categorization, the AI can go through that normalization problem because it can interpret that it is about the same topic or about the same species through its training data. The second part is, through all of these databases, you get an idea on what is known about an invasive species like this, but there will always be gaps in there. And then comes the second part, which is the research mode. And what the research mode does is it will find through AI multiple sources, it will extract the information of what is interesting to the user, and then we'll put that inside of that aggregated database. So you eventually have a full report, what is more whole and not in multiple locations, but just by one click of a button, theoretically. What were some of the challenges while we were making this tool? Well, all of the information needs to be completely traceable. We need to make sure that all of the original authors can be credited, but also that everything can be fact-checked. An hallucination in a report like this can be quite detrimental, because if it says that that red crayfish really thrives in temperatures in 20 degrees and above, but it completely made that up, kind of a problem. And the second challenge that we had was that the tool is made for a lot of different experts. Some of them might need policies, while others need simple facts about where this species thrives in. So the salinity, the temperature, etc. So all of them need to be able to interact with this tool. And the third that we have is, at a certain point, this tool is done. So we wanted to open source this so this tool can keep on growing. And invasive species is a problem not only from Europe, which is the GuardES project, but it's a worldwide problem. So everyone can eventually copy this tool and use it however they see fit. Thank you.
Morning, everyone, or afternoon, actually. My name is Ime, and associate professor from Victoria University, Wellington, and the Center for Data Science and AI. Today, I'm going to talk about some recent work from our group about learning traffic signal control policies. I guess people have been, if you have been driving, then you will be annoyed by these traffic jams. And maybe sometimes you will see you have been waiting for a long time in a traffic light, but it never turns green without any reason. So you're just wondering how this traffic control policy works. And this is what we are trying to use machine learning to help. So what has been doing by the researchers so far? Of course, traditional methods for traffic signal control based on fixed time intervals or some manual rules. They are easy, intuitive, but couldn't fit very well in the highly dynamic real-world traffic scenarios. And then machine learning or deep reinforcement learning methods. People have been trying those approaches. And these reinforcement learning methods could work well sometimes, but they could be quite complex, black box, and hard to interpret, explain, and also the network tends to be complex and large and make it harder to deploy. But at the same time, the generalization to unseen scenarios of these reinforcement learning methods could also be an issue. And this is why we are considering, a genetic evolutionary machine learning approach, genetic programming. Or before that, this deployability issue of, deep learning methods. It can be, complex, not fast enough, and, also because of the space limit of the small device that you need to put on the traffic lights. And the deep network usually cannot fit the size, the capacity of this device. Like this one, all these orange dots are those complex machine learning models, and they are outside the box, meaning they need to be reduced. Their size needs to be reduced. But after simplification of this neural network, you will get some degradation of the performance. And explainability also, deep neural network, black box would be hard to explain. And that's why, genetic programming, that's what we are considering, could be good in both deployability and explainability. And I guess, you have seen some presentations about genetic programming based on evolution, Darwinian evolution and evolving models. I think I don't need to go into details, but this is a rough, illustration of how we evolve the models that could be potential effective traffic signal control policies. So this is kind of a roadmap of our work so far. We proposed the first approach called GP Light, Genetic Programming for Traffic Light, and we published it on Gecko last year and won the Best Paper Award in the Genetic Programming track. And that's kind of the baseline approach for we can use genetic programming to learn an effective traffic signal control policy. And later on, we further improve this model by considering addressing the inconsistency of the urgency between the phases. And so as a result, whichever phase, which means the combination of the green lights, this GP light plus, no matter which order of the green lights put into the model as the input, GP light plus will always produce the same output. And this was published in Transactions on Evolutionary Computation this year. And later on, we further extend the work by considering heterogeneous intersections, not just these crossroads, but also other types of T-shape or more complex intersection shapes. And also, we consider communications between different intersections rather than just each intersection make its own decisions. And we also did some extension work, and then we would, in the future, further consider more real-world factors such as, different durations of the phase. Some phases might have, 30 seconds or 1 minute, and so on. And I'm going to show some, performance. This is on a benchmark intersection. And, our results are much better than an existing machine reinforcement learning method called MP Light. And the smaller the better. This is the waiting time of the traffic. And another video shows the a real world map. And this is a more complex intersection, and we can see the above is our GP Light model, and below is an existing policy, circle-based policy, and you can see how they behave differently and how that can make the above policy can make the traffic flow more smoothly. Okay, that's the end. Finally, we have some contributions, social benefits. We know how that's important for the traffic, for the CO2 emission and efficiency, and for the driver's mental health, and also as well as other benefits like lower resource consumption. And we also have our program reproducible by scanning this QR code. That's all. Thank you very much.